Hello and welcome to our webinar, Commercial Rooftop Units in Minnesota, Their Characteristics and Energy Performance. We would like to take a moment to recognize the Minnesota Department of Commerce's Conservation Applied Research and Development Program. This project was made possible by funding from this amazing program. Today's presenters are myself, Scott Sheeter. I'm a senior engineer at 7th Wave, and Mark Hancock, the Director of Engineering at CEE. Today we'll be going over the following: a brief background and objective, the characterization work undertaken by 7th Wave, the monitoring work undertaken by CEE, and finally some program considerations. We'll kick off with some background and the objective of this research project. Heating, ventilation, and air conditioning, or HVAC, energy consumption comprises just over 30% of U.S. commercial building energy costs. Within this considerable footprint, packaged RTUs serve nearly half of this region's commercial floor area. But what is an RTU? For the purposes of this study, we define RTUs as a forced air HVAC system that packages the evaporator, condenser, and heating coils into a single unit that serves the building's heating, cooling, and ventilation loads. Note that this study does not therefore include dedicated outdoor air systems, makeup air units, or heating-only units. RTUs are ubiquitous on commercial buildings throughout the U.S. due to their low capital cost, reliability, and well-developed service and distribution network. There is some evidence, however, that these systems may operate inefficiently and suboptimally. To better understand these systems, we conducted a multi-level field study to characterize the RTUs in Minnesota. The results of this study may be used to improve or develop utility conservation improvement programs whose goal is to reduce the energy consumption of new and existing RTUs. Now let's cover in a little more depth the methodology of the characterization. We had to selectively sample a set of the RTUs in Minnesota. This sample needed to be large enough to be statistically significant, such that the results were representative of all the RTUs in Minnesota. However, it couldn't be so large that we couldn't find all of the data within the scope of the project. Our approach, therefore, focused on a random sampling methodology according to the following: develop a subset of Minnesota zip codes, identify all the buildings in each zip code that had RTUs using publicly available satellite imagery, like Google Maps. Find the contact information of a subset of these buildings. Then conduct phone interviews with a subset of those buildings, collecting data about the buildings themselves and the RTUs that serve them. Analyze the data and extrapolate that back to Minnesota as a whole. We began by using U.S. Census Bureau data to randomly sample 50 of the 936 total Minnesota zip codes, which are shown here in red. Our sampled zip codes ranged in size, density, and geographic location. The yellow dots represent the buildings where we conducted interviews with facility staff and are discussed in more detail subsequently. For each of these 50 zip codes, we then used public aerial imagery to systematically search for all the commercial buildings with RTUs within a given zip code. For each of the buildings where we identified RTUs, we counted the number of apparent RTUs and gave the building an identification code and associated place mark. Here we see all of the place marks for an urban zip code and an example of one of the buildings with RTUs. Here's another zip code, this time much more rural. As you can expect, it took much longer to enumerate the urban zip codes than the rural zip codes. The enumeration process identified a total of approximately 4,500 buildings across the 50 zip codes, with an initial count of nearly 29,000 RTUs. And that's a lot of time spent counting RTUs. And during all that time, we saw some other interesting things besides RTUs. A few of the more memorable examples include someone who took the time to write their name in a field with a backhoe, presumably, lots of outdoor hockey rinks, of course, and renewable energy installations in the form of large photovoltaic arrays and utilities-grade wind turbines. We also saw a plane on the approach to land at Minneapolis-St. Paul International Airport, and my favorite was a corn maze in the shape of a locomotive. The next step in our process was to identify the contact information of a portion of these buildings. Using this contact information, we reached out to each building and attempted to connect with someone who would be able to provide us with pertinent building and RTU data. We completed a total of 87 interviews. For these buildings, we collected a lot of data, most notably for the buildings, their age, size, location, occupied schedule, and maintenance practices. For RTUs, we collected their age, heating and cooling capacity, and heating and cooling efficiency, as well as information about the compressors and fans. We also collected information about the new and replacement market through AHRI data and interviews with major RTU manufacturers. This data included annual shipments and sales, the efficiency level of the RTUs, and their refrigerant type. Taken together, all of this data was then extrapolated to characterize both the existing and new RTUs in Minnesota. Now that you understand our process and the data we gathered, let's dive into the results of the characterization. First, we'll cover the buildings served by RTUs. We estimate that RTUs serve 20,700 Minnesota buildings. That's 1 in every 6 commercial buildings in Minnesota. In total, that's 730 million square feet of commercial floor area, or equivalent to 450 of the new Viking Stadium. Here we see a histogram showing the number of buildings by decade built. Nearly a third, or 30%, of buildings are relatively new, having been built since the turn of the century. However, buildings fall into each decade in significant numbers going back as far as the 1950s. Interestingly, the oldest building in our study was built in 1881, and it's safe to say that its RTUs aren't original to that building. Another interesting finding of the study was in regards to the number of buildings versus building area. Smaller buildings, those less than 50,000 square feet, dominate the total number of buildings, comprising 78% of all buildings. However, larger buildings, those greater than 50,000 square feet, dominate the total area of buildings, comprising 70% of total square feet. That's interesting because as a program, you can affect a lot of the total area with a smaller set of customers. However, to get to more and more RTUs becomes increasingly difficult. RTUs serve every major commercial building type. The type of building the RTU is serving significantly affects its energy consumption, as building with higher internal loads such as food service or food sales require different amounts of HVAC energy than more sparsely loaded buildings such as warehouses. The building types with the highest number of buildings are office, food service, food sales, and public order and safety. Combined, these building types comprise over half of the buildings with RTUs in Minnesota. However, in terms of area served by RTUs, food service, food sales, and public order and safety are a much smaller portion due to their relatively small average area per building. However, warehouse and education increase their share due to their higher average area per building. Offices remain significant by area. When planning programs, it's useful to know where the technology of interest is located. We therefore categorize the buildings served by RTUs by their location, whether they were in the Twin Cities, the surrounding suburbs, or greater Minnesota. Over half of buildings served by RTUs are in the Twin Cities or surrounding suburbs, which include the 7-county metro area. Some other building characteristics that we found along the way include routine maintenance has been shown to increase RTU performance. We found that over half use contracted vendors for maintenance purposes. Although this is likely the highest level of maintenance, program opportunities for improvement exist through training of trade allies regarding proper maintenance techniques. We also asked about the frequency with which filters were changed and condensers were cleaned. A common recommendation is that air filters be changed on a quarterly basis. Over half of buildings had air filters changed less frequently than this recommendation. Condensers were even less likely to be cleaned on a frequent basis, with over 1/3 never being cleaned. Different owner types may make decisions that affect RTU performance based on different criteria. For instance, people that own their buildings, as well as those that manage a publicly held building, may have more motivation to invest in energy efficiency than those that lease their space. This is presumably because they may evaluate investments on a longer time horizon and may directly see the benefits of improved energy performance in terms of reduced energy costs. We found that over 4/5 of buildings were owner-occupied or public. Many buildings have multiple associated businesses. As opposed to buildings with a single tenant, buildings with multiple tenants may be more difficult to approach programmatically, as they often require the additional step of connecting with the management organization. We found that over 2/3 of buildings had a single tenant. Approximately 1/5 experienced comfort complaints based on RTU performance. Some reasons for comfort complaints include the fact that the system was broken but subsequently repaired, the system was undersized and therefore unable to maintain thermostat set points, improper air distribution potentially due to a single RTU serving multiple zones, or perhaps someone remote to the building itself, such as at the headquarters of a retail chain, controlling the set points and not taking occupant feedback into consideration. Now I'll outline the characterization results of the existing RTUs. We estimate that there are approximately 136,000 RTUs serving Minnesota buildings. This equates to 6 per building on average. 3 manufacturers account for approximately 3/4 of the RTUs in Minnesota and over half of the installed capacity. For those buildings that had more than 1 RTU per building, nearly 2/3 of the buildings had RTUs for multiple manufacturers, which is a surprising result to me. The age of RTUs also has an impact on energy performance, because newer RTUs may have higher efficiencies and system performance tends to degrade over time. The average age of an existing RTU in Minnesota is 13.1 years. Newer RTUs, or those that are less than 5 years old, comprise 11% of existing RTUs. Also, only 7% of existing RTUs are older than the Minnesota Technical Reference Manual's value of 20 years for estimated useful life. The total estimated cooling capacity of RTUs in Minnesota is approximately 1.3 million tons, with an average cooling capacity of 10.7 tons per RTU. That total tonnage is equivalent to the amount of cooling you'd get from melting the ice filling over 470 Olympic-sized swimming pools in 1 hour. Slightly more than half of the individual RTUs have a cooling capacity of less than 5.4 tons. Another third have a cooling capacity less than 11.3 tons. However, RTUs with cooling capacities over 20 tons comprise 45% of the cooling capacity of all RTUs. Another way of putting that is that there are a lot of small RTUs, but the bigger RTUs have lots of capacity, even though there are fewer of them. The RTUs in Minnesota are overwhelmingly air-cooled. None of the RTUs we characterized were water source or ground source heat pumps. Only 3 RTUs were identified as being evaporatively cooled, all of which had very large cooling capacities of 170 tons. The full load cooling efficiency is currently the major driver of how much electricity an RTU consumes. The average full load cooling efficiency of RTUs in Minnesota is 10.6 EER. There's a clear trend of increasing cooling efficiency in newer RTUs. In fact, over the last 20 years, the average cooling efficiency of RTUs has increased by 18%. For new construction or renovation projects, the Minnesota Energy Code requires a minimum level of cooling efficiency for RTUs. The requirement varies by cooling capacity range. It is therefore interesting to compare the average cooling efficiency within each of these cooling capacity ranges. On this graph, the existing RTU data are plotted as bars. Additionally, the range of cooling efficiency between the current Minnesota Energy Code and Consortium of Energy Efficiency's Tier 2 recommendations for high-performing RTUs are also plotted to illustrate the potential programmatic savings magnitude. In RTUs with cooling capacities below 20 tons, the average existing efficiency is below the code minimum and well below the Tier 2 recommendation, suggesting considerable opportunity for improved efficiency in smaller RTUs. For larger RTUs with cooling capacities between 20 and 63.5 tons, the average existing efficiency is between the code minimum requirement and below the Tier 2 recommendation. Since their efficiency is already relatively high, there is a limited opportunity for increasing efficiency. For the largest capacity RTUs with cooling capacities above 63.3 tons, the average existing efficiency is near the Tier 2 recommendation, leaving little opportunity for increased efficiency. The current trend in increasing RTU performance is with respect to part load cooling efficiency rather than full load cooling efficiency. For instance, variable speed compressors, often inverter driven, allow for part load efficiencies over 18 IEER. We calculate that 30% of existing RTUs in Minnesota have some level of part load efficiency, and that proportion is increasing. For existing RTUs in Minnesota with part load cooling efficiencies, the average IEER is 11.2. The total estimated heating capacity of RTUs in Minnesota is approximately 24 million MBH, with an average heating capacity of 205 MBH per RTU. Nearly 3/4 of individual RTUs have a heating capacity less than 225 MBH. However, RTUs with heating capacities over 225 MBH comprise 58% of the heating capacity of all RTUs. We found that the heating fuel type of Minnesota RTUs is overwhelmingly natural gas fired. The remainder use electric resistance heating. The average heating efficiency of natural gas fired RTUs in Minnesota is essentially the code minimum required value across all capacities. That's approximately 80%. We did not find any high efficiency condensing rooftop units, as they are a relatively new but growing technology. The fan speed is an important characteristic influencing how much fan energy an RTU consumes. Single-speed fans are used on 4/5 of RTUs in Minnesota, representing 56% of total RTU fan power. A large and growing proportion of RTUs use variable speed fans, comprising 42% of fan power. The relatively large proportion of variable speed by fan power, as opposed to number of RTUs, is indicative of the higher incremental cost of variable speed being more justifiable in larger fans. Now we'll cover the characterization results for the new and replacement RTUs. We estimate that a total of 6,400 RTUs are shipped to commercial buildings in Minnesota annually. Of these, 40% are for new construction projects, while 60% are for existing retrofits or replacements. This estimate represents approximately 4.7% of our estimated existing RTUs. We further estimate that the total sales of RTUs in Minnesota was $88 million annually, which is approximately 0.03% of Minnesota's gross domestic product. Using the proportions from our manufacturer interviews, we estimate that 3,500 shipments are for code-compliant RTUs, while 2,900 shipments are for high-performance RTUs. These levels of shipments represent $41 million and $47 million in sales for code-compliant and high-performance, respectively. We also analyzed new construction data to ascertain what types of commercial buildings were being built in Minnesota that are likely to include RTUs. We determined the following mix of commercial buildings by square footage that were built or planned to be built in Minnesota from 2013 to 2016. There's a clear trend of rapid growth in the lodging sector. Over the past several years, this is driven by growth in multifamily, assisted living, and hotels and motels. Although RTUs are not typically applied to multifamily buildings, opportunities are certainly available for efficiency programs to increase RTU efficiency on the other lodging building types. Two sectors with strong growth were healthcare and education. Again, both not traditionally known for using RTUs. However, RTUs do serve portions of each sector, and such institutions' longer-term mindset suggests they may be more open to improved energy performance, even if it means increased capital costs. Office spaces remain a large sector for growth, and with their high use of RTUs remains a significant opportunity for programs. Warehouses round out the sectors with the most growth. Although a portion of warehouses are not typically conditioned, those warehouse spaces that are conditioned have high use of RTUs. I'd like to turn over the presentation to Mark at CE to discuss the monitoring portion of the project.
Okay, thank you, Scott. So CE performed the monitoring phase of the work. As Scott had mentioned, Seventh Wave was doing mainly characterization. CE was looking at the monitoring. The things that I'd like to touch on today is to talk a little bit about the in-depth site visits that we performed, look at the information from the site visits, how we determined where we found sites to be monitored, talk a little bit about that monitoring protocol that we use to collect the electric and gas consumption, some results of the data. We also did a evaluation of oversizing, and then talk a little bit about the key performance indicators. So the in-depth site visits were the main goal behind that was to get information, more detailed information that could be collected from the characterization phase. We wanted to get boots on the ground in these sites and take a look at the condition of the RTU. We wanted to look at the evidence of service, see if there's any operational issues with the devices. And when I mean devices, I talk about the fan, the compressors, the sections of the units that are providing service to the space. And in the space, we also wanted to document the occupancy, the thermostat type, and the distribution system that's happening within the site. As Scott had mentioned, he had 4,500 buildings in the total characterization study. We've narrowed that down to about 80. He narrowed that down to 87 that there were phone interviewed, and of those 87, there was potential 43 sites that we could use for in-depth monitoring. That is characterized by the left side of this slide. It shows distribution of the sites that were potential sites for in-depth, and once we contacted those sites, we were able to secure 20 sites for actual in-depth site monitoring. Those sites are shown on the right side. And as Scott had mentioned, 57% of all rooftop units are within the Minneapolis metropolitan area. So this does give a good sampling of the rooftop units that we would see. Some of the things that we saw on the rooftop units were the good and the bad, and this kind of gives you indication of what we were looking at. On the left side here, we're looking at a few pictures of rooftop units that we consider to be in pretty good condition. The upper left picture is a rooftop unit that doesn't have any damage. The casing is in good shape. The middle picture shows the compressors and the heat exchange area that is well maintained, well cleaned, and the wiring in that area is also well maintained and clean. On the right side, you get a little bit of an indication of things we saw that were bad. The upper right-hand picture shows excessive amount of hail damage to the condensers, the dust that's associated with not maintaining the unit. This is a pretty good indication that not much is happening with regard to maintenance on this particular unit. And the rightmost picture on the lower right shows a damper that's just not functioning very well. And if you can see very closely there, you can also see that there is kind of misapplied filters there. They're overlapping one another. So we saw quite a variety of good and bad in the space. For the RTU devices themselves, we were looking at the components of the systems. So we were looking at the condition of the fans, whether they were direct drive or, in the case of the upper picture here, the belt drive. We also looked at the economizer, and we looked at the general condition of the compressor and heating section, again, on that left side. To give you a little taste of some of the tests we were doing on the rooftop units, we had an economizer test that was definitely a test that was, it teased out the information of whether the economizers were working. We had three main tests that we did on the economizer test, and that was a power down test, which was we removed power from the rooftop unit to see if the damper moved from a position of minimum to closed, which it should if it would operate normally. We also did a minimum outdoor air adjustment test where we adjusted the screw on the controls to see if the controller signaled the motor actuator on the economizer to move the economizer damper. And then the last test we did was an ice pack test where we attempted to try to trick the RTU into thinking the conditions were right for economizing if they weren't right during the site visit, and see if economizing could happen. So as you can tell from these economizer tests, these are very definitive tests. They either did work or didn't work. More subjective tests that we had done are a condenser airflow test. And we passed our hands across the condenser fans to see if airflow is even across the face of the condenser fans. And this is a good indicator of whether the condenser coils themselves are plugged or not. In the event that the airflow is plugged, the condenser fans will set up more of an annular flow where the flow of the air will exit the outside of the fan and then enter into the center of the fan because the fan tries to achieve airflow even if the condenser fans are plugged. So these are some examples of the tests that we did. Moving from the roof, we moved into the space within the building to look at what type of spaces these rooftop units were supplying. The three pictures on the left of my slide here show typical spaces that we encountered. So we're seeing a meeting area, an open office with a relatively light density in the upper picture. The middle picture is definitely a very highly occupied building. It's just an example of a call center. These are types of spaces that we could have incurred. And then the bottom is a picture of a industrial site. So we really wanted to know what type of sites or what type of spaces the rooftop units were supplying as part of the in-depth site visits. We also were documenting the thermostats that control the rooftop units in the middle of this slide. The uppermost thermostat is a standard thermostat, has no setback. The middle thermostat is a programmable thermostat that has a lockbox. It gives us a good indicator that there won't be any set point fluctuations or they will be consistently set. And then the bottom thermostat, there is a Wi-Fi enabled thermostat, and we ran into a few of those at our test sites. The rightmost pictures are documenting the air distribution within the site. We wanted to know what type of air distribution was happening within the site. Do we have a false ceiling with a return air plenum, or a suspended ceiling, I should say, or do we have an open ductwork? So these are the types of information that we collected. And I did want to note too that I have a lot of information to move through here, and there's a lot more detail in the report. So I encourage you to download this if you are interested in further information. So the results of the in-depth site visit, as I'd mentioned, we had 20 sites that we visited. We documented 93 rooftop units for all the tests that we were performing. And because this was the sites did not get compensated for participating, it was just their goodwill to let us into their buildings and to document their information. There was no correlation that we could find between the capacity of the business type or the area or the space use. And it wasn't a statistically significant sample. It was just the ability to go and get an in-depth site visit from these sites that were a subset of the characterization grouping. As there's no shock here, but what we found is that the older the RTU, the lower the condition score is, or the worse the condition of the rooftop unit is. The roof is a very harsh environment. It is extremely hot in the summer, and in the state of Minnesota, it gets extremely cold in the winter. So rooftops do take a beating, and the older they get, the more beat up and the lower conditional score they got. Some of the other information that we collected as a result of the in-depth site visit was to document the economizers. And of the economizers that we looked at, Honeywell was predominantly the economizer manufacturer controller that was used. And then as I referenced from the 3 tests that we did before, only 36, or about a third of the units tested, passed all 3 tests that we performed on them, which is an indication of, economizers still have some area that need to be looked at. A smaller subset, only 10%, I should say, failed all the tests. So there is a good indicator out there that economizers are still failing. One of the things that I did want to mention too was that over 80% of the outdoor air minimum settings for all the rooftop units in the in-depth site visits had a setting of less than 10%. And that's indicative of a lot of rooftop units in Minnesota. 10% is sort of the value that a lot of designers use for outdoor air volumes, but we saw a lot of rooftop units that had 0 for their minimum outdoor air settings. The thermostats that we saw out there, over half of them were programmable. That's a good indicator that there is opportunity there, or at least people are taking opportunity to install these programmable thermostats. There was still a significant amount, around 16% non-programmable, that are just set 24/7, 365 days a year. And then 30% had a building automation system, and this was primarily from one site that had a large number of rooftop units that did have a building automation system. But I want to remind you that the in-depth site visits were there to collect information regarding what was happening in those sites. But the main focus of the in-depth site visits was to try to figure out if we could get a number of rooftop units to do long-term consumption monitoring. So once we have the rooftop units identified for consumption monitoring, or at least the sites, I should say, how do we get at this consumption data? The 2 main energy streams that we're looking for in rooftop units are the gas consumption and the electrical consumption. Traditionally, if you were to put a standard logger on the roof and install a gas meter, redo the gas lines in order to get the gas consumption, and then also install a power meter, that's going to be an extremely expensive endeavor when you start looking at the number of rooftop units and sites that we wanted to monitor. So CE took a different approach where we decided to time the gas valve. By knowing how long the gas valve is operational, and by knowing the input rate of that gas valve, we were able to compute the energy consumption of the gas for the rooftop unit. And we also deployed a single CT transformer method to measure the energy consumption on the electrical side. The single CT transformer, or single transformer method, has been used successfully in a number of other research projects, and we did extensive research on how to implement that measurement. To get away from that standard logging, we just selected a internet-based logger that was able to establish local communications between the rooftop units and a cellular gateway, and then use cellular communication to go back to CE's data collection servers in order to collect the data in near real time. So we were able to get data pretty accurately and pretty quickly to understand how the consumption of the units were working, and really to check on our monitoring system. Here's an example of there's 2 pictures of the monitoring equipment. The lower left shows the pulse counter with the red tape on it, and then the pulse generator, which is hooked in parallel to the gas valve, which gives us a pulse rate whenever the gas valve is active. The upper right-hand corner shows the current transformer on that brown wire, and then the wireless sensor that's measuring the 0 to 5 volt DC signal that's coming from that current transformer. So the energy consumption data was pulled back. It was summed for an entire day and then related to outdoor air temperature. And we were looking for two basic models that are set up for energy consumption. And the primary models are the electric, which has a change point, and above that change point to the right is a cooling component, and to the left is generally just the fan component. In the gas model, it's generally just a linear curve, So the energy consumption of a rooftop unit is primarily driven by just outdoor air temperature, ambient outdoor air temperature. So from the in-depth sites, we were able to get 9 sites that agreed to have us monitor their energy use. These space types were a variety of offices, churches, light manufacturing, and we also had a restaurant. We had a total of 52 rooftop units. They ranged in size from 3 tons to 15 tons. And I did say that we had the ability to collect data at a very high rate, but we did run into some problems with our monitoring. We had some communication issues, and we also had some sensor issues that our manufacturer was not even aware of. So we didn't get the data capture rates that we really wanted to, but we did get very accurate data that spanned all temperature ranges. So most RTUs had at least 150 days of data. I wanted to show you a few graphs now to depict the energy consumption that we saw across the sites. I also want to tell you that every rooftop unit got these type of graphs generated. So if you do go to the report, you'll see a lot of graphs like this. So this is a very clean gas graph where you see the red lines are the energy consumption during the weekday period and the energy consumption in the weekend period. You'll see that the R squared is very good. It's around 90% or better for both. So I consider this to be a very good gas model. Conversely, we have another site here where we have what's happening is just the opposite, where we have weekend consumption is actually higher than the weekday consumption. That could be attributed to the fact that the space has heat requirements that won't be met without the people or the activity in the space. Here's a rooftop unit that didn't use any gas whatsoever. It was an interior space. We did test it a number of times to make sure the gas was activated and could be activated from the thermostat, but surrounding rooftop units could have been carrying this load for this particular rooftop. And here's a model that follows no predictable path. There's too much varying loads that are happening within the space to even develop any type of correlation between outdoor air temperature and energy use. So we were able to compute the annual energy consumption from the rooftop units models. We developed the models with outdoor air temperature and then applied the model to typical meteorological year data, or TMY data. And we were able to look at what the energy consumption was of the rooftop unit as opposed to what the site consumption was. And the site, we used 12 months of energy data, monthly energy bills, and I report here the observed, which is the actual, and then we developed a model and applied the TMY data to figure out what the modeled consumption was. And you can see in the case of many of these sites, the energy consumption for the rooftop units was at least 100% or close to 100% was attributed to the rooftop units, which is typical for these types of spaces where the rooftop is the predominantly used gas-using appliance. The one exception to this rule is the DAV site, you'll note here in the middle, that had only 20% rooftop unit. The DAV site is a restaurant, so there's a number of commercial cooking equipment that uses gas within that facility, and with dishwashing, they have a pretty high water load also, I would assume. So shifting to the electrical graphs, we look at the change point models for the electric graphs, and here is another example of a very clean model that shows a good relation between outdoor air temperature and weekday, weekend periods where you have a change, or you don't have any cooling that activates until a change point of about 60 degrees for this particular unit, and then a relatively flat consumption below 60 degrees, which is attributed to the fan energy. Another site that has no indication of weekday, weekend change. This has energy use that's pretty predictable. It did have a programmable thermostat, but it was not changing the values sufficiently enough to show difference. And here's our site that I mentioned before, which is the restaurant site. There's no difference in weekday, weekend, which probably you would expect for a restaurant type facility, but What's interesting here is that the change point for this model is at 45 degrees. So mechanical cooling is being initiated above 45 degrees, which for me, that tells me the economizers are not working properly for this particular unit. So just as the gas consumption, we compared the electrical consumption of the units with the electrical consumption at the site. And again, we're looking at a variable of what's happening within the site. Is the varying range between 25 to 50% rooftop unit to site energy consumption, with no real indicator of whether there is a correlation between a site type and a energy consumption of a rooftop unit. So once we had this data, we wanted to look at the ability to evaluate sizing considerations for rooftop units. Traditionally, if you wanted to look at sizing for a rooftop unit, you would compute the internal heat loads, the heat requirements, the cooling requirements, and then assess your building envelope for heat loss. We weren't able to do that just because we didn't have a lot of information on the building components itself. So we elected to use the actual monitor data to evaluate the sizing of the rooftop unit. We would develop from the interval data, 15-minute data, we would look at the energy consumption as a function of outside air temperature, develop a model, and then apply the design cooling and heating temperatures to those two separate models and evaluate the energy consumption at design conditions. To give you an indication of whether we had design temperature or not, this is a plot of outdoor air temperature that was experienced during the monitoring period, and you can see during the heating period, that's during the shaded red area, we did experience a few times in the interval data that we achieved design temperatures, and then further to the right, we had a number of days where we had the cooling design temperature, which is depicted by the more shaded blue area. These are the results of the capacity at design conditions for the gas data. This is the heating percentage at capacity or at design for the gas use. And if you drop all these points down onto the x-axis, you will see that they all reside somewhere below 40%. The majority of them are landing. We decided to plot the annual energy use plotted against the heating percent of capacity to give you a good indication. And there's no surprise there that once the unit uses or is closer to design, it uses a little bit more energy use. If we looked at the electric side, we're closer to design capacity on the electric side. These units are much more sized appropriately for the space. We did have a number of units that expanded beyond the 100% value, but that was just an anomaly that had to do with the extrapolation of the regression lines as a result of the models and applying the design temperatures. So what we learned is heating is definitely oversized more often than cooling, but that's not a surprise when you start thinking about a rooftop unit. There's not a lot of people out there that look for a rooftop unit or size a rooftop unit for the heating capacity. It's generally sized for the cooling capacity. If you're going to reference a rooftop unit, you're not usually going to call it a 250,000 BTU per hour rooftop unit. You're probably going to call it a 10-ton rooftop unit. So if you size it for cooling, you generally get whatever heating capacity you get from the manufacturer. And if you were to select heating capacity, I'm sure it would take a lot of extra time in order to get that unit from the manufacturer to your site and probably incur additional costs. And as an example, I show you some heating and cooling percent of capacity for one site. And you see that there are areas that have pretty close to capacity, referencing rooftop unit 8 and rooftop unit number 9. But those were exterior zones that had south-facing facades that had a lot of external heating and cooling requirements. whereas rooftop units 1, 2, and 3 had interior zones and didn't have a lot of heating requirements. So lastly, we wanted to try to tease out performance indicators from this data. And the reality is that we didn't have a lot of performance indicators that we could get from this small sample set. There was a wide variety of space types, a wide variety of RTU capacities. This made it very difficult to identify a key performance indicator. Space set points were changing, and the capacity per area of floor area shifted quite a bit between sites. So I think one of the takeaways is it's very difficult to identify a key performance indicator from a rooftop unit because there's no application for rooftop units, or I should say no consistent application for rooftop units at a wide variety of sites. But one thing that did come out of this was that economizers continue to be a problem, and this is consistent with what we found, or what other researchers have found across the country, that economizers fail due to lack of maintenance. They even fail because they're not set up appropriately. They have the inappropriate set points that don't allow them to economize. So I think that pretty much wraps up the monitoring phase of things. I'm going to hand it back to Scott, and he'll close this out.
All right, thanks, Mark. And to round out the presentation, we'll talk a little bit about some program considerations. Manufacturers are offering new products and features that continually increase the available efficiency options for new RTUs. Although this list isn't comprehensive, it represents some of the larger opportunities for savings. The main trend for increasing RTU energy performance is in increasing its part load efficiency through the use of variable speed and variable capacity components and associated controls. These systems have the added benefit of increased humidity control, which therefore increases occupant comfort as well as energy performance. Variable air volume capabilities, as opposed to the current standard constant volume systems, are becoming available on increasingly smaller capacities. Improved economizers ensure that the outdoor air dampers do not let in unconditioned air when closed. And advanced fault detection also ensures that the economizer is working properly. Condensing gas-fired heat exchangers capture the latent heat in the combustion exhaust, increasing the heating efficiency of gas-fired RTUs from 80% to approximately 90 to 95%. Increasingly, sophisticated intelligent controls are also being applied to RTUs. These controls are capable of precisely controlling RTU operation to optimize energy performance, as well as detect faults and alert maintenance staff to address degraded performance quickly. Currently, the Minnesota TRM contains two RTU-related measures, cooling efficiency and economizer measures. Both of these measures focus on electric consumption savings. A review of Minnesota programs found prescriptive rebates available for RTU cooling efficiency, demand control ventilation, and energy recovery ventilation. Expanding the TRM to include a wider scope of RTU-related measures will aid in the development of more comprehensive RTU programs. The incremental cost is a major barrier to improve performance. This barrier is addressed programmatically through rebates to defer a portion of the incremental cost of higher efficiency units. Historically, these rebates have been based on exceeding a minimum full load efficiency. Since the trend in efficiency for RTUs is increasing part load efficiency, developing rebates based on IEER would be beneficial. Building owners and design teams have limited time and resources to spend on understanding and interfacing with utility efficiency programs. Therefore, clear and simple program requirements will increase program participation. Some other additional insights we gathered from our interviews with stakeholders include recasting rebates in units that are more understandable. Prescriptive rebates have traditionally been based on RTU cooling capacity, such as $75 per ton. This aligns well with the energy savings, which scale with cooling capacity. However, it is not a metric that most building owners understand. Potentially recasting rebates based on square foot would make the rebates more understandable from a program participant perspective. It can also be more readily incorporated into project budgeting as it sends a consistent upfront signal. Programs can reduce transactional costs of participating in programs with less time via less paperwork and more online simple interactions. Stabilizing incentives, as it is confusing to program participants and trade allies when incentives run out or change. Additionally, educating trade allies such as manufacturers and distributors is a good idea. You can educate them about the program so they can be more easily embed the program information into their process. They can be further supported with simple tools and calculators for calculating available rebates, as well as energy and utility cost savings. Since expected RTU performance is often not achieved without proper commissioning, requiring some level of commissioning, such as that its inclusion in contractor reports, will help ensure energy savings. Programs can also ensure proper RTU installation to achieve expected levels of performance. The Air Conditioning Contractors of America have developed guidance for proper installation. This standard also includes recommendations for owner training, which is important for ensuring persistence and high levels of energy performance and savings. In conclusion, RTUs are a significant component of commercial building energy consumption in Minnesota. This project clarifies the existing RTUs and the opportunities for effectively improving their performance. Thanks for your time. I believe we have some time now remaining to address a few questions.
And the first question is, which you may have answered, could you describe any common faults you found that led to increased energy consumption?
Well, I would say the main thing that we found that increased energy consumption, and it's primarily the cooling, is the fault of the economizers. When you look through the graphs of the energy consumption, the electrical energy consumption as a function of outside air temperature, get a real quick indicator real fast when you see cooler air temperatures and excessive energy use, which is indicative of the compressors running. So economizers were definitely the thing that had the most indicator of energy consumption.
And then a follow-up question onto that. Are there any things that a facility manager can look for to catch these issues as they occur?
Well, a facility manager is somewhat of a loaded question because the building types that we're dealing with here, they don't typically have facility managers. They have somebody they call up when something happens. Rooftop units in and of themselves are those ugly boxes that are on the roof. The owners of those rooftop units don't necessarily know what's happening up there, and hopefully they care enough to get a contractor involved to get regular maintenance. But there's not a lot of indication of whether it's performing good or bad. As long as it's still maintaining a heating and cooling set point, the facility or the people within the site won't know anything unless they go up there and look at it. But you do need to do regular cleaning of the condenser coils. You need to change out your filters. If you're exposed to hail damage, you need to get those things replaced. Those will make sure your rooftop units are operating at their peak performance.
Great, and then I think we have time for one final question, which was, what were the important factors that you used to determine which sites to actually monitor out of the potential sites that you had identified?
Well, the reality is that it was looking for sites that would agree to be monitored. We did not have a statistically significant sample where we were looking for a number of offices, a number of light industrial, a number of restaurants. We were given a relatively small sample set, and we were trying to find sites that were willing to allow us to monitor. So there was no effort really given for getting a statistically significant sample in any one building type or any one rooftop unit type. This is just a broad stroke to understand how these rooftop units work in the particular sites that we did have the opportunity to monitor at.
Great, and I think we're running up against time now, so I'd like to thank everybody for their time. And like a reminder, we'll be following up with more information about the final report and links to the on-demand webinar. Have a good rest of your day, and goodbye.